Hello, my name is Joel Schneider, and in this lesson I'd like to talk with you about divergence theorem. There's a visual analogy that explains why the divergence theorem works the way it does that I find really helpful, and I'd like to show it to you. And then we'll go through some applications of the divergence theorem and some practice problems. The divergence theorem examines the outward flux over a closed surface. And let's see if there's an easier way to calculate this rather than finding a bunch of surface integrals. Let's start with a very generic closed surface, say a cube, and we want to look at the outward flux through this cube. I'm going to show you sort of a visual representation of the divergence theorem so we can get some intuition as to why the divergence theorem works and what it actually says. So let's imagine that I cut this cube in half with this orange horizontal slice, and now I look at the outward fluxes over both of these individual halves. Well, you can see on the outside faces of the cube, we have exactly the same fluxes that we had in the original cube. The only thing that's different in this situation is now we have two additional faces on the orange slice that have been exposed. But if you look at the top half and the bottom half, they're exactly the same surface, measuring exactly the same flux, except their normal vectors are pointing in opposite directions. That means the flux over one of these orange faces is going to be identical to the flux over the other face, except it's going to be negated. That means if we add these fluxes together, they'll just cancel out and we'll be left with zero. That means that the flux over the original cube is the same as the sum of the outward fluxes over these two halves. If I wanted to take this a little bit further, we could cut it again in the vertical direction using this green slice. If I use the same logic, since the green slice's fluxes have normal vectors that point in opposite directions, those will cancel out as well when I add them. So that means that the flux out of the original cube is the same as the flux over each of these individual four cubes all added together. Let's say that I cut it vertically again, but in this purple direction here. Now we have 8 pieces, all much smaller than the original cube, but I can still say that the total outward flux over all of these 8 pieces added together is the same as the total outward flux for this big piece at the end. We can repeat this logic over and over and over again, dividing our cube into smaller and smaller pieces. Eventually, we'll get that the total outward flux is the sum of an infinite number of infinitesimal little cubes with differential side lengths dx, dy, and dz. If we're trying to find the flux of a vector field f, denoted as m, n, p, we calculated in class that the outward flux over this cube is equal to partial m partial x plus partial n partial y plus partial p partial z times dx, dy, dz. We denoted the sum of these partial derivatives as del dot f. This is noted as the divergence. We can remember that because dot starts with a d, as does divergence. And then finally, because we have a cube, we can write dx, dy, dz as dv. So that means that the total flux over the entire cube is the sum over the volume of the divergence of f times dv. So now let's look at what the divergence theorem actually says. On the left-hand side, we have the surface integral over a closed surface of f dot n hat ds. And on the right-hand side, we have the triple integral over the volume of the divergence of f times dv. This left-hand side is the overall outward flux over the closed surface, like we talked about before with our cube. Instead of calculating that, we are rewriting it as the sum over the volume of a bunch of smaller fluxes. Some things that are important to note when we're using the divergence theorem is we must have a closed surface. So sometimes it will be helpful if we have an open surface, specifically to close it so that we can use the divergence theorem. We'll go over a practice problem of that in a minute. In addition, it's also useful to note that the divergence theorem allows us to have an integral that changes its type. We start as a surface integral and we convert it to a volume integral. As I'm sure you found out, calculating surface integrals can get rather complicated, but calculating triple integrals is much more straightforward, so oftentimes the divergence theorem will simplify our calculations quite a lot. The other way we can think about the divergence theorem is seeing how divergence measures sources and sinks. If we're trying to figure out how much stuff is flowing out of our cube, we can look at every single point inside the cube and see whether that point is a source or a sink. And if we add up the total amount of sources and sinks inside the cube, then that has to give us the net change or flow of stuff out through the surface of the cube. Now let's see if we can apply this divergence theorem to the sphere problem we had earlier and make sure that we are answered, and double check that our answers agree. So we wanted to find the flux of this vector field out of our sphere of radius 2. Now instead of directly calculating n hat and ds in our surface integral, let's rewrite it as the triple integral over the volume of the divergence of f dv. If we calculate the divergence of f, it's going to be partial with respect to x of the x-coordinate plus the partial with respect to y of the y-coordinate plus the partial with respect to z of the z-coordinate. This is equal to 1 plus 1 plus 1, which is 3. So that says that the total outward flux is equal to the triple integral over the volume of 3 dv. Well, since we have a constant integrand, we can say that this is equal to 3 times the volume. We know that the volume of a sphere is equal to 4/3 pi r cubed, so we can substitute our radius of 2 to get 4 pi times 2 cubed. This gives us a final answer of 32 pi, just like we had before, so our answers check out. As a final problem, let's look at making sure that our surfaces are closed and seeing if we can use this to our advantage in solving unclosed surface problems. Let's look at the paraboloid problem we had earlier with the same vector field f that we've been dealing with in all of our problems and the surface S, z equals 4 minus x squared minus y squared above the xy plane. Here is our picture again, and imagine that we close our surface with a disk on the bottom in the xy plane. Now our closed surface has two parts that we put together to make the closed surface. It has the disk on the bottom, which is S1, and it has the curved paraboloid on top, which is S2. We are only interested in finding the flux over S2, but in order to be able to use a divergence theorem, we need to have a closed surface, so we need to temporarily add S1. Let's take a look at what this actually means for our calculations. We want to find the double integral over the surface, S2, of f dot n hat ds. Well, that would be the same thing as the surface integral over the entire closed surface, S1 and S2 together, and then subtracting out the surface integral over S1. What does the vector field look like on S1? Well, S1 lies in the xy plane, which means that z equals 0. That means that on S1, our vector field has no vertical component whatsoever. But if we look at our normal vector only has a vertical component. Well, that means that the flux through S1 has to be 0. So since the flux through S1 is 0, we're just left with the total closed surface integral over S1 and S2. So if we can find that closed surface integral, then we know that our answer is going to be the same thing as just the integral over S2. Now that we have a closed surface integral, we can rewrite it as the triple integral over the volume using divergence theorem. Since we're working with the same vector field as in the previous problem, we already found the divergence is equal to 3. So we can plug that in and get that our total surface integral is equal to 3 times the triple integral over the volume of dv. So finding the total volume doesn't come offhand as a formula that we already know, so we have to actually calculate it. Well, we have a paraboloid that is symmetric around the z-axis by rotation. This makes sense if we were to use cylindrical coordinates. We already have an x squared and a y squared in the equation of our paraboloid, so if we choose cylindrical coordinates, our overall surface will become z equals 4 minus r squared. If we rewrite our integral, we'll have a 3 out front, and our dv becomes r dz dr d theta. Now what are our bounds? For constant r and theta, the minimum value for z is always 0, and our maximum value is always the paraboloid on top, which is 4 minus r squared. We project everything down into the r theta plane, and we're just left with a circle. So that means that our bounds for r are 0 to 2, and the bounds for theta are 0 to 2 pi. If we evaluate the final integral, we'll get an answer of 24 pi, which checks out with our previous answer. And we're done. I hope that this video helped to summarize the concepts behind the divergence theorem and surface integrals, as well as how to calculate surface integrals. We started by looking at how we can use the divergence theorem to convert those surface integrals into triple integrals, which are even easier to calculate because the divergence generally simplifies the numbers involved in our problem. We also looked at how we can use the closed surface restriction to our advantage, so now we can use the divergence theorem to solve any type of open surface problem as long as we remember to manually close the surface. Thanks for watching!